We're going to be working with page 249, and in page 249 we're going to be reviewing an example that would illustrate the concept of continuous growth. Okay? So I want to remind you that I would like you to listen to this video after you have listened and worked with activity 3.7, since activity 3.7 is going to introduce the concept of logs, and we're going to learn, or we're going to use the concept of logs to understand the concept of continuous growth. So in page 249 I have a word problem that talks about the growth of the US population. I know the US Census has reported that the population of the US for April 1st of the year 2000 is 281,421,906 people. We also have the population for the year 2001, and in the 2001 we have this many people. Okay, so if we assume exponential growth, the US population should be or can be modeled with a function that is written in this form: a times b to the t. Now, t would be the number of years since my t equals 0. So what I'm going to do, I'm going to assume that t equals 0 represents the year 2000. So since I know that my starting value is my population in the year where t is equals to 0, what that means is that I already have a, right? That I can go ahead and start writing my function because I already have a. But I need b, yes? So what I'm going to do is I'm going to find b. Now, remember that b is your annual growth factor, and b is represented by the ratio of outputs connected to consecutive inputs. So if I divide the population in the year 2001 by the population in the year 2000, right? Remember that these are consecutive years, and you can do this in your calculator. You're going to get 1.01. This number right here is B, which is my annual growth factor. Okay? Now, remember that there is such a thing as the annual growth factor and the annual growth rate. Okay? So this is my annual growth factor. How do I find the rate? Well, remember that B is 1 plus R. That means that R is B minus 1. So if I subtract 1 from 1.01, I'm going to get my annual growth rate. My annual growth rate will be 1.01, which is, given as a percent, is 1%. That's my annual growth rate. So I can go ahead and write my equation. I'm going to come right here and I'm going to write my equation. My equation would be y is equal 281,421,906 times my b, right? And my b is 0.01 to the t. Okay, so that represents my exponential function that is modeling the US population as a function of t. Now, you know that the US population did not remain constant from April 1st, 2000 to March 31st, 2001, and then jump to another number in April 1st, 2001. In other words, that population didn't grow by jumping, it grows continuously. So it makes sense to think about modeling this growth by way of a continuous growth. So let me remember about the formula that I know that models continuous compounding for an investment. We just learned that in 3.5. The formula that grows continuous compounding for an investment is A is equals P times, I hope that you remember E to the RT. Yes, I can also write it as P times E to the R, we'll put a parenthesis to the T. Okay, so this E to the R seems to be the base of my exponential function. So this is continuous compounding for an investment. So what I need to do is I'm going to write the formula for continuous growth. Okay, in other words, this is the formula that I'm going to use to model the growth of population. So my formula will be y is equals, right? It will be y is equals a, the same a that I have right here. I'm going to use exactly the same a, and will be e to the kt. Okay, so the same function y equals b to the t will be represented as y equals a times e to the kt. And again, I'm going to write it as a times e to the k to the t. Now, who is a? A, again, is my starting value. My starting value. Yeah, let me erase these points right here. Okay, and who is K? Who is K? Well, K is the continuous growth rate. Yes, so K is the continuous growth rate. And we all know that E is my irrational number. My irrational number. Again, I'm going to model this function on the top of this function. So let me write it now, my new function. My new function will be equals to, my A is the same, 281,000 million rather, 421,906 times e to the k to the t. Now my problem is who is to the k? Who is e to the k? Or who is k? If I do e to the k equals 1.01, you remember your logs, k would be ln or natural log of 1.01. K would be the number 0.00995. You can find this number in your calculator. Yes? So my function will be y equals 281,421,906 times e to the 0.0095 to the t. Okay? And this is the representation of my exponential function. So what did we learn today? We learned that we can represent exponential growth as a times b to the t when b is greater than 1, and we can represent continuous growth as a times e to the kt. E to the k is equals to b, and to find k, I'm going to find ln of b. This is the end of the first video for activity 3.6.